come down to the rows here in front, please. Test 1, 2. Okay. Okay, welcome everybody. Welcome to Physics of Semiconductor Devices, part of physics-based technologies. I'm Dr. Verrelli. You know me already. We've met in the labs. Obviously, I had a surprise for you, which I believe is pleasant. We have our friend here, which is recording. So just a few words about it. I'm planning to record myself and nothing more. I have the microphone is here. I'm going to record just my voice. The microphone is close to me. Hopefully, nobody else's voices will be recorded. There is a matter of privacy or whatever. So I'm aware of that, and so I will do everything that is in my power to obviously avoid that any one of you goes on record. So please do not pass in front of the camera now that it is recording. The camera will be pointed to the whiteboard, and the computer is also recording as an inset at the top, just to grab myself at the board. Okay, so you will see when I upload the video what it is like. So the idea is just myself. I will appear on the video. Okay, I don't want any one of you to ever appear on the video for the reasons I've said. Is there anyone that is against of me recording my lecture? Please speak now. Okay, so we are all happy with this. I'm happy with this, so we are happy. So what will happen then with the videos is I have a YouTube page where I'm already using YouTube for my nanoelectronics for the level 7. The videos are uploaded as unlisted. This means that only the people that have the link can actually see the videos. You cannot search the video. Okay, this is just for again another level of safety, let's say. So I will upload the link. I will actually put the link on Canvas. So you will then be able to access the video through that. It's clear? Okay, good. Okay, so just a few words. I've made a Canvas page for our course yesterday, and so maybe some of you have already had the chance to have a look. I wanted just to say a few words very briefly, if I can get Canvas here, just to clarify some things. Oh, first of all, immediately on assessment. So my module is all assessed with the exam. So 50% of your overall mark is through my exam, my questions in the exam. For the other submodule, the one nonlinear optics from Dr. Kelly, 30% will be through the exam, 20% through homeworks. Okay. So physics-based technologies. So here, these are the two submodules. So if you click on any one of these two links, you go to the module pages, and there you can read more in details. This is the general features of what the module is about. And here is the assessment strategy that I just briefly mentioned. Okay, 50%. So in the exam, you will have basically a total, the weight will be 80%, split 50% for myself, 30% for the other submodule, and you have this 20% through homeworks for the other submodule. So let me have a look now at our physics semiconductor devices. So as you know, 2 hours per week for the first 10 weeks. It's very unfortunate that we'll be not always in one lecture theater, but I understand that we'll be kind of moving around between this and another one, I think in Larkin, I can't remember. Which I find it a bit unfortunate, especially because I have to set up all this equipment. Anyway, we will deal with that. And take a note of my office hours. You can come to my office to ask for anything at any time, really. If you come at these hours, it's maybe more probable that you'll find me there. Otherwise, it's better always to drop an email. Regarding the specifics now of the module, so there is something that I always remind students, the 20 credit system, 20 credit, works like this. Effectively, this corresponds to a certain amount of work that the student, the learner, is expected to do. And this amount of work that corresponds to this is around 200 hours. So each module corresponds to so many hours of work from your side. This comprises everything: exam, revision, lectures, everything. So let's have a look at this module. So you have 44 hours lectures, which are split in half between me and Dr. Keller. You will have an exam, which is 2 hours. Let's say you have a revision to do, obviously, at the end. Let's say now, very roughly, 44 hours, the equivalent of the lectures. So very, very roughly now, this is 100 hours. This immediately means that there are 100 hours missing. What are these 100 hours? I know you know it. It's the work that you have to put during the 12 weeks on your own into these modules. Every module in total for the module. So I'm expecting you to work 50 hours, roughly, again, 50 hours for physics of semiconductor devices, and 50 hours for nonlinear optics. How much is this, 50 hours in 12 weeks? Let's say, very roughly again, 4 hours. Very roughly, 4 hours. Okay? And this is true for all modules. This means, be careful, this approach means that ideally, if you were able to do that for every module, you have 3, 4 modules, at the end, you would be fine. Okay, so that's why in this page, what I'm saying is, please try to be ahead of what we do. Work also on your own. It is very important. Okay, this is an advice that you should take for all modules generally. Do not wait. Work ahead. And in here, especially for this module, I will be relying on this, because here, what I want to do is mainly I would like to focus on exercises. Okay, there is no point for me coming here and staying with the back to you, blah, blah, blah. There is no point. Okay, you will switch off in 5 minutes. Then you go home. What he was talking about? Okay, well, I would like to make, more things that are interesting, exercise. But to do this, you have to do something on your own. Okay? So that's why I'm also recording, so that you have, something to work on your own. Yeah, I think I had something else to say at this point, but it will come to my mind. Okay, so very roughly we have the material is split in 4 chapters. So the beginning is really, something that I think you should know probably, at least to some extent. So very broadly about electronics, chapter 1, signal system, circuit analysis. We'll spend probably 2 weeks, so this week, this lecture and the next lecture. Semiconductors, again, a couple of weeks on that. PN junctions, and then bipolar junction transistor. This completes 10 weeks, and then we will have the tutorial. This is very roughly the plan. And here, this is the schedule for you, based on what I just said. So you can see here that today, well, very roughly, I will be going from signals to circuit analysis included. Okay. Next week, AC circuit analysis to the end, basically, of chapter 1. Okay, no linear circuits and so on and so on. So I would like you to read this lecture plan and see what I'm about to do, let's say, in that lecture, in any lecture, and try to be ahead of me. So on your own, try to follow the material that I will describe in a moment, and try to, work on your own based on that approach. So the material now, I don't have PowerPoints. Okay, that's why also I'm recording. And I will use the whiteboard. But behind this module, there has been months of research, let's put it this way, to find material that is, first of all, online, ebooks, all is freely available through the library or something, that is simple enough without any crazy formalism or, thousands of integrals and, something that is, you can do on your own, okay? I literally spent 4 months looking through 37 or 38, I don't remember now the number, different online resources available either through the library. I'm using also the MIT OpenCourseWare. So MIT has an online portal where they put all the lectures they have. So I'm using also those. So you'll see them. Actually there, I'm telling you, they have also video lectures. So it's a very nice place to look at. So MIT OpenCourseWare is cited in here anyway. So here below the lecture plan is the detailed course content. So these are all the references. Every entry that we are going to discuss here. So for example, today, analog and digital signals, blah, blah, blah. Every entry has the corresponding link to some resource. And it's very detailed. So for example, I have here this example that explains the resources. Kirchhoff laws, you can find them in reference 12, chapter 1, section 1.6. Or I explained this here. Reference 12 means is the link to the ebook, to the total ebook. Then you have to click on chapter 1. And so please read in great detail these instructions I'm giving you. It's very important that you use these properly. The numbers means nothing. These are my numbers while I was going through the 38, 40 resources. So the numbers don't mean nothing for you, but are unique numbers. So if you see 12 somewhere down the line again, it's the same resource. That's what I mean. Okay? All right. So this was briefly what I wanted to tell you about for this, the structure of this submodule. Now, what is this submodule about? You've done, I'm sure, through these 3 years you are here, electronics to some extent. I know, for example, in the second year you've done some semiconductor physics. I know that you haven't done it in great depth. I know also that you've done some electronics. Actually, today I discovered that this was quite a pleasant surprise. So transistor characterization. This is a lab, first year lab. So that was quite a nice surprise. So you do BJT. That's what we will do basically at the end of the course. So bipolar junction transistor. So obviously there is no, this was not done in the sense that we will do it here, investigating in depth what's the physics behind, how it works. But the end of this some module is to obviously understand the physics behind semiconductor devices, having an emphasis especially to these two that are very key components, the PN junction and the bipolar junction transistor, but also see applications of those. So do circuits. That's why we need this initial chapter about circuit analysis, to make sure we have good basis on circuit analysis. We will not do anything crazy. Our circuits will be generally simple. Okay, so I won't go through crazy analysis, or there is no reason. It's only an algebraic difficulty there, nothing more. So that's why, don't worry about that, if you ever worried about it. But there is one thing that we should stress. Why do I want to study PN junctions and BJTs? We may have an idea of why they may be important, but the reason is all the electronics we've done until today, maybe in the lab, in simple circumstances, is all what we call linear circuits. Then the point in this course is that we will be learning how to deal with heavy nonlinear circuits, the PN junction, the BJT. So that's the key. Okay, so we will going a step further in this sense. How do we deal with nonlinear components? Okay, this was my opening statement, and let's start. Okay, so the detailed content material that is on Canvas is actually what the schedule will follow, the time will follow here. Okay, literally, in sequence. All right, so you can also rely on that, knowing what to know what I will be doing. So first of all, signals. Let's make some drawings here. So I will draw with what type of signals are generally we deal with in the lab. For example, a voltage signal. Okay, a voltage V in time. Now we can immediately realize there are several situations. One is this one. This is time, and this is V. There may be another situation where this looks like that. Or maybe there is another situation in which it looks like that. Now it's not very easy to do. So let's say what they are. So this is clearly continuous on the abscissa, sorry, ordinate, and continuous on the abscissa. Continuous in time, continuous on the voltage. It is definitely discrete in time. Unfortunately, here the plot doesn't allow me to emphasize the difference, but this was also continuous. I can take any value on V. Okay, so this is continuous V, continuous time. This is continuous V, discrete time. This one here is, I've emphasized the steps. So this is clearly discrete V. Now, I did not draw regular intervals probably, and I did it in purpose. So unfortunately, my drawing here is impossible to be too precise. If you go to the reference I'm using, you will see much better. So here the point is that these intervals here are not the same, okay? So that's why it's continuous in time. Time can be any. Now here is the situation where you have discrete both. Discrete voltage, discrete time. So really we have these four situations in general, okay? Some are more relevant for circuits that we may call digital, where what we call digital circuits are those where the voltage is discrete. I'm sure you've come across digital circuits. It's where the voltage, for example, can only take specific values. So really, these two cases down here point to digital circuits, either discrete in time or continuous in time. Actually, in this course, we will be dealing with the top two, those where we can call the systems analog, where the voltage, or anyway the variables involved, are continuous. Voltage, current, and so on and so forth. So these are analog systems that we deal with. Okay, so you will probably find today's lecture, you will probably find yourself thinking, oh, I know this thing. So I will try to go in a way to keep the pace up, if I can, so that you will not be bored by this initial part. But I think the main point for me of doing this is to make sure that we are all on the same page, okay? So to make sure that we have good basis for what will happen next, in the next lectures. So actually today's lecture will be probably things that for you are actually revision. I've actually marked, if you go and look at the material, I've marked those things that I think for you are revision with a yes, revision. So today is mostly about these things. So let us remind ourselves what is a periodic function. So if I have a signal, xt, an analog signal now, we've decided to work with analog signal. What is the definition of this being periodic? What is the condition you would impose? It has to repeat itself in time, isn't it? With a period t, that we call t, the period. So the condition I would impose is that xt isn't it? This is the condition of a periodic function for any t. So once we define period, if you remember, obviously, I'm sure you've done these things already many times, we define frequency as the inverse of the period. Remember, the period is measured in seconds. The frequency is measured, the inverse of second, which is called the hertz. And then we can define also the angular frequency, omega 2 pi f, which is measured in radians per second. In reality, obviously, you know that radians is not a real unit. Yeah.
Does that mean n is equal to like the normal integer like 1, 2, and 3?
Sorry, n is integer, you're right. Correct. And also can also be negative, actually. Yeah, okay, so. Okay. It seems that could be, there is some light reflection on the board. Anyway, we'll judge the result of the video, yeah?
What's the thing next to it there?
This means for every. For every n. It's mathematics, formalism, I don't know. Okay, so let's move on. So what do we mean? So once we have a periodic function, let us say that y is a periodic function. What do we mean by average? How do we calculate the average? In general, the average over time t is given by this. This is the general definition, isn't it? Obviously, in case of a periodic function, this is actually 0. I'm sure you've done this in several times, if it was a sinusoidal function or a cosine or so, whatever. Now, in the specific case of periodic functions, because they have an average that is 0, we define another average, which is meaningful, and we call the RMS value, where RMS stands for root mean square. And the definition is exactly what I've just said. So it is the average, is the square root of the average of y squared. And so I use now that definition to do again, for a periodic function, we said that the average is 0. How much is y RMS for a periodic function? For a periodic function that is average 0. So if we assume that we are dealing with, so let me do it more clearly. I'll write it here to be more clear. So if we assume now that I have y equal a cosine omega t, then we can demonstrate that the average of y of this function is 0, and the y RMS value is a over square root. Okay, these are some very simple results that you can demonstrate in no time using this definition. Probably you've already come across these things. Okay, let's move on. How are you feeling? All right? Okay, sorry it's a bit boring, but just, you know, make sure that these are things that we have clear in our head. Okay, now, may I? Okay. Now, let us assume, this is a very important definition now, just to have clear why up until now you've been dealing with the linear system. What's the definition of a linear system? So, linear system. So let's assume that this is my electronic system. A system, it doesn't matter if it is electronic actually. A system S that takes some input xt and gives out yt. How do we define that it is linear? It must satisfy two fundamental functions, properties, sorry. The first one, it has to be homogeneous. What does it mean? It means that if we assume that for xt input we have in output yt, then if I have m xt in input, the output must be myt. This is the homogeneous property. The other property, which is equally important, is to be additive. This means that if x1 t is the input and y1 t is the output, and x2 t is the input with y2 t the output, then if I have as an input x1 plus x2, the output will be y1 the additive property. Okay. These two could actually be summarized by saying that I can take a linear combination of x1 and x2 with some parameters, a1 and a2, and the output has to be the linear combination of blah, blah. I prefer to leave them separately so that we have, you are able to see that there are actually two properties at play, homogeneous, additive. Let's see them in action, okay? Let's take some system that relates an input to an output. For example, let us assume that my system is a system that does this. Takes an input, it multiplies it by a constant, and gives it an output. Could be, I don't know, in electronics, it could be an amplifier. Let's demonstrate that this is linear. So let's start from the homogeneous condition. If I take m xt and I give it an input, what I will get out? I will get k m xt, which I can rewrite as m. I'm obviously exaggerating here, overemphasizing it. But this is y, isn't it? So it is homogeneous. Let's demonstrate. So I will write it here as homogeneous. Sorry, this is a tick. Additive. So we have x1, for which we know that the output is y1, and x2, for which we know the output is y2. So this means that for x1, the output in this case is k x1, which we call y1, and for x2, this system gives k x2, which we said we call y2. So now the question is, if I take x1 plus x2, and I give it an input to the system, the output will be k x1 plus x2, which is k x1 plus k x2, which is, obviously you can see now that this is y1 and y2, so this is y1 plus y2. Okay, so this satisfies both, so it is linear. It's a linear system. Obviously, this was an extremely simple case of a linear system. You can think of many others, but I would like to show you one that is non-linear. So let's have a look at one that is non-linear. Can I remove this? I'll remove this one. Now we know anyway the definition. So let's have a look at a non-linear case. Let's assume that my system does this thing. Let's test the homogeneous property. So I take m xt as an input. The output is e to k m xt, which I can write as e to k xt So this thing is obviously different from what I would have wanted if it was homogeneous. I would have wanted to get y, isn't it? Yt. So this bit is what we call, sorry. I've jumped one step and it messed up everything. So this point here means that this is equal to yt to the m. While we said that the output we would have wanted if it was homogeneous, so this is different from what we wanted, that is m yt. So this is definitely not homogeneous, If my aim was to demonstrate that it's nonlinear, I've already finished because it's not homogeneous, so I'm done. Okay? You can also demonstrate that it's non-additive, obviously because of the exponential bit. Okay? So just to clarify the definition. This is very important, and obviously, you know, it can be a very nice exam question. Actually, just because I mentioned the exam, obviously there are 4 chapters. There will be, you know, one little question, chapter 1, one little question, chapter 2, and, you know, chapter 3 and 4 are a bit more important. So, okay, but roughly, just to tell you, we will touch all the chapters in the exam. Okay, another important, very important property of systems in general, and especially for us, electronic systems, is, so just to check that we are still recording. When you go and watch the video, you'll see me go close with my face. Okay, so another very important property, this was linearity. The other very important property is time invariance. So obviously system can be time invariant or time variant. Obviously the term explains already what these terms mean. So let's see what do we mean by time invariant. So we have our system S, and this is xt, and this is yt, so time invariant. So the system is time invariant if, knowing that xt has as an output yt, then we can demonstrate a delayed version of that signal gives as an output a delayed version of the output. This is what we call a delayed version. Has been delayed by an amount tau. Just if you wanted to see this in action, I mean this delay thing, so xt, let's say that xt is this, a step. And the step happens when t is equal to 0. Xt minus tau means that the step will happen at tau. So that's the difference of a delayed signal. Okay, so this system that is time invariant has the property that if you delay a little bit the time at which whatever signal goes in input, also the output is automatically just delayed. This effectively means something very profound on how the system behaves. You see, generally when we wrote this, when we wrote down this diagram here, we are not saying what as is. In general, though, in very general terms, what are the variables at play here? Well, definitely it's time, and is the input, and whatever else, parameters, whatever is inside, but definitely 2 variables, time and the input, xt. So in the most general approach, I could say that yt is s of time by itself, and xt, the input. This is in the most general approach I could take. What this time invariance is actually telling us is that the system does not depend just on time. This is not at play here on its own. It's only through the signal. So it's a very delicate point. Okay, but it's very important. We'll see this in action now with an example. Does it make sense? Do we have 2 variables here? Time by itself, in general, and the input signal, that is a function of time itself. But the system itself may have, for any reason, its own time dependence in the response. Okay, so this is the in-depth meaning of time invariance, that the system does not have any straight dependence on time. The only dependence on time comes through whatever signal I'm applying to it. Let's see this in action. So I will remove and this is true for any signal, obviously. Okay, let's make an example. Previously, we saw an example of a linear system. Let's see if it is time invariant. Previously, we've seen this one. This is linear, for sure. We've demonstrated that. Let's see if it's time invariant. So I consider this is an input. What will be the output? K, x t minus tau, which is, according to this definition, y of t minus tau. This was extremely simple, obviously. So this is also time invariant. Time invariant. Let's see an example that is non-time invariant. So let us consider this system. I'll use here a tau star just because we are using tau in the definition there. Okay, so if I take x t minus tau as an input, the output will be k. So at this point, here is the key point. Remember, I'm delaying the input only. I'm not touching the system. You see, this term here is the key. I can't delay this thing. It's not in my, how to say, I cannot touch it, cannot reach it. It's not approachable by me. It's related to the system. And so you understand that this is the problem now. Because this is not y t minus tau. Because this y t minus tau would have been, I need just to go back here and substitute t with t minus tau. So this will be k so you can clearly see that the problem is exactly there. Okay, they are different. Okay, so this is time invariance. Now, all the electronic circuits you've probably come in contact with up until now are all linear and time invariant systems. Okay. For most of the circuits we will deal with, they are all time invariant. But on the linearity, obviously, there will be a problem, and that's what we will deal with. Okay, let's move on. How would you define an electronic circuit? What would be? You have to explain tell some. What is an electronic circuit? What have you ever, tried to define it? You can find some definitions here and there. In the reference I've put in the material, there is a definition that I find, concise and interesting. It summarizes nicely. So an electronic circuit is an ensemble of components connected together for the conversion, transmission, and storage of energy. I like these three terms: conversion, transmission, and storage. Okay? It's a definition I like. So this is in the reference I put there. Okay. So we are now entering a little by little, you know, how we deal now with circuits. Once we've you know, analyzed, you know, signals, a little bit of definitions on systems and so on. So if we take we will have a break at 10 to 3 in 5 minutes. So if I have pieces of conductors, for example, of materials connected together, and I wanted to analyze this circuit, we've said what is an electronic circuit. Imagine you were Kirchhoff, or I don't know, Volta, or when, you know, all this thing was at the beginning. Ideally, you would have had, probably not to do so back in time, but let's say Maxwell. What Maxwell would have had to do was probably use the Maxwell equations to deal with that. Because that's the way you deal with electric fields, magnetic fields, with induction, and so on and so forth. All phenomena that are at play with the electronic circuits. So there are two main equations that probably you would want to deal with. And the first one is the continuity equation. And the other one is the Faraday lens, effectively. Where phi is the flux linkage, magnetic flux linkage, because of external sources, while Q internal is any charge that is internal to the circuit. Imagine the circuit as a tube, if you like. If you go to the reference, they are exactly what they do. So what this is saying is that within my circuit, where S is the surface of this enclosed tube, of this tube. This is the surface of the tube, or maybe we should consider just a piece of that to explain this concept. So if I take a piece of material and there is some current going through, we will discuss in a moment, you know, exactly the definition of J, but this is current anyway. So there will be some current going in and some current going out. This is saying that the integral over the entire surface of this piece of material has to be equal to the change in time of the charge internal to this piece of conductor. At the same time, this one here is dealing with a loop. So imagine now that we have a loop where we have many of these pieces of material connected together. And this is saying is the lens, Faraday lens law. So if there is a magnetic field around that is changing with time, the external flux linkage with the loop, there will be an electromotive force created. That will equal the integral of the electric field along the circuit. So that's Maxwell equations. Oh, this looks very complicated to use to solve an electronic circuit, isn't it? It's very complicated. But that's in principle what you should do. The thing is, and this is the whole point why I'm trying to adventure myself in these things, is that there is some fundamental assumptions that we do when we deal with electronic circuits, and allows you to, for example, write V equal R time I for Ohm's law, or allows you to use Kirchhoff voltage law or Kirchhoff current law, and so on and so forth. And there are two assumptions that we do at this point. And the assumptions are these two. We will assume that the components we deal with are such that this is 0. This means that there is no charge, there is no variation in time of the charge in here. So that what this will allow, effectively, what goes in, goes out. So the current going into a component also comes out. Does this ring a bell? Kirchhoff's current law. So this assumption by itself is the reason why we use Kirchhoff current law, which we will write in a moment. Do you understand this? Huh? So the other assumption that we will do is that, so this is quite interesting, because this is saying that I have a circuit, but there may be something external to that circuit that I have no control of, that I even don't know where it is, but it could cause something, could cause an electromotive force. So our assumption when we deal with electronic circuits, and we will deal with we will derive maybe the equations we deal with, is that I know everything of the universe outside this circuit. And there is no, I can guarantee that there is no electromagnetic field that could cause a flux, a flux linkage variation with the circuit. So there are no, this effectively means that if there is any source in the circuit, I know it, and is there because it has to be there. It's not caused by an external factor. And obviously you understand that the conclusion of this is that Kirchhoff's voltage law, okay, which we will discuss after the break in 10 minutes. If you want a break, otherwise I would like a break, at least 5 minutes.
Yeah.